Good evening, ladies and gentlemen. Thank you all for being here. I am Saleh Achraf, Risk Manager and QHSE of SOMAS, Société Marocaine de Stockage. And lately, I have been involved in H2 underground storage development as the H2 underground project manager. Today, we will explore a promising solution for the storage of hydrogen as the world seeks out new renewable and cleaner energy and more sustainable. The hydrogen becomes a key player. And one of the challenges and crucial challenges of the H2 is the storage. Which has to be efficient and safe. And that's where the salt cavern come into play. By the end of this session, you will have a deeper information and understanding of this technology and the opportunities that presents, and also the challenges that poses and how it fits into the broader energy landscape. For this task, please welcome our distinguished speakers. We have here Professor Abdelaziz MRIDEKH, the Professor of Geology at University Ibn Tofail of Kenitra. He's a distinguished researcher in geology fields, including geophysics, structural geology, geodynamics, and seismology, among others. Also, we have in the panel Frank DERRIEN, a business development manager in energy chain at Storengy. He has more than 30 years of experience in the field, and lately he focuses on the development of hydrogen markets. And via Skype, via Zoom, we have Mr. Jesús Manuel JIMENEZ, hydrogen director at Enagas with more than 25 years of experience in the oil and gas industry, and also focusing lately since 2017 to develop the H2 market in Spain, and he's also responsible for all the engineering and the modelization of the hydrogen market backbone in Spain. So, just a brief presentation of SOMAS, Société Marocaine de Stockage. It has 50 years of experience in the storage of oil and gas products, notably LPG, this unique technology, which is the salt caverns. And you can see the photo. It's a real 3D imaging of one of our caverns. And our vision for the future is to make available our expertise and our infrastructure to the energy transition here in Morocco, and to prove the concept and to make sure that we will play a big part in the hydrogen economy. Okay. Just a quick salt cavern overview. So the salt caverns are a man-made structure in salt deposits. How the process of creating such caverns is we have petroleum oil gas typical well that we drill in the ground to reach the salt deposits, and then by a process of leaching, we inject water, and water dissolves the salt, and then by a process of circulating the brine, we create that space, and you can see the evolution. You have the three stages as a sonar imagery, the first, the second, and the last volume that we created in one of our caverns. What are the benefits of such technology? It's secure and stable. It's suitable for various products. We can have such example as storing oil, storing hydrogen and LPG and so on. Also petrochemicals and even waste management. And it has a very low environmental impact if we compare it to traditional way of storing like spheric tanks. So to deep dive in this topic, we have three main questions that we need to address during this session. What are the advantages of using the salt caverns compared to other methods? What are the capacity potentials? And what does it align with what we are projecting for the future of hydrogen markets? And of course, what are the risk and safety concerns about this type of storage? So let's deep dive in this topic with the power of science. And I invite Professor Abdelaziz to give us a much scientific insight about this topic. Thank you.
Thank you very much, Achraf. Hello, everybody. I'm very happy to be with you in this session to present you some of our first results about discovering the potential of storing hydrogen in the underground. Our results are part of our MRIDEKH projects, which we are working on with our colleagues from HDF, Enagas, SOMAS, ONIM, and Green Park Energy. I'm a professor at Ibn Tofail University. I'm a geomechanician, geophysician, and other specialties. So, just let's have a look about underground storage. It's not new for industrials. They have also tested natural gas storage since the beginning of the last century. And in 2017, data showed that 50% of natural gas was stored in salt cavern. This is why the amount of knowledge and experience on hydrogen storage is minimal. We are in the phase of exploring this style of storing. Even though we have 1,019 salt caverns worldwide, which are used in storing natural gas. So if we look to the existing salt cavities, we have only about six examples worldwide, 3 in UK and 3 or 4 in the United States. The one existing in UK have a volume of 2 cubic million meter and a depth of 400 meters under approximately pressure of 50 bar. As my colleague Achraf has said before, storing hydrogen in the underground has lots of advantages, some disadvantages, but most advantages are safety. They are far from attack from surface and natural risk, only where regions are under seismic risk, like we have seen last week here in Marrakech region. We can have a variety of in the volume accessible in space. It's depend of the volume of salt and their spatial distribution. It's low cost. Just after establishing these cavities, it's used for a long time, and the existence of salt is proven in lots of places of the world. So, beside using salt cavern in storage hydrogen, there is also some structures, some underground structures which can be used. Namely, we can use depleted oil and gas reservoirs, and we can use also aquifers, that's main layers in which there was brine water or fresh water. I will make a moment a comparison between these style of storage. Let's have a look about the geology of salt. Salt or rock evaporites are special type of rocks. They exist in some places in the world. Morocco has the chance to have large places where we have these kind of deposits. I will show in a moment a map of Morocco where we have lots of places where we have a huge salt deposit. Geologically, salts are minor components of sedimentary sequences. It means that salt exists with other kind of rocks. During their deposits, they can have a very large manner to be deposited. We call that in geological language, environmental deposits. We can have a large platform or basins or lots of configurations. This means that in terms of volume, the volume of salt will vary from place to place. And the characteristic, the most characteristic of salt, it does after its deposition, it began another way of life under a regional stress. As you know now that Earth is never stable, it is moving all the time. And with this movement, salt underwent a lot of movement under regional stress. And the configuration of salt or salt can take a lot of configuration, depends of the nature of stress applied on salt layer. I have put some examples of salt configuration in the underground, and the processes or mechanism or deformation can be as follows: halokinesis, differential loading, contraction, thermal convection, gravity-driven expansion and extension. Just to say that studies now are divided between two kinds of underground hydrogen storage, or salt cavern done in horizontal layers, and salt cavern which are done in salt dome deposit. In Morocco, we have both. And as my colleague Achraf has said before, salt caverns are created by solution mining, by injection of fresh or seawater. And in Morocco, we have all the western part, from Agadir to Casablanca, we have lots of sites where we have salt deposits, both onshore and offshore. So the potential for salt underground deposit is really very huge. Worldwide, the depth and geometry of salt deposits are very large. We can have salt cavity from less than 500 meters to 2,000 meters depth, and ancient evaporate basin worldwide can have lots of geometry, as you can see in the right of this of the slide. So if we want to make a comparison between salt cavities, aquifers, and depleted reservoir, we can see that from the formation point of view, salt cavities are man-made. That means that we must create this cavity by solution mining, whereas aquifers are natural media where we can put hydrogen in the void of the rocks. As for the depleted reservoir, for the geological setting salt cavities are salt formation within sedimentary layers, whereas aquifers and depleted reservoir exists in structured terrains or deformed terrains. And the storage capacity for salt cavity is largely more or developed, can be more developed than the aquifers and depleted reservoir. Here we can have some measurement of depth in salt cavern, in depleted reservoir, and in depleted reservoirs. And at the end of my speech, I will just give some idea about risk related to hydrogen storage in salt cavity. The first risk is ignition and degradation of material during the contact between hydrogen and facilities of the well. The second risk is the risk of microfracturing of the rocks or the rocks that is in contact with the hydrogen, and the third is hydrogen leakage. So two parameters must be taken during the exploration of salt rocks to develop them to salt cavity: stability concerning fractures and spatial distribution concerning the volume. Thank you very much.
Thank you, Professor, for this comprehensive and very precise presentation about the science behind the salt cavern. Now I invite Mr. Jesús, connecting with us from Spain, and to give us his insight and opinion about the topic.
Hello, good afternoon. Can you hear me?
Yes, we do perfectly.
Okay, great. Well, first of all, thank you very much for the invitation. So sorry because it was impossible finally for me to be there with you, but I'm having seen all the event and all the presentations in different plenary sessions and so on, and I want to express my congratulations for the event and all the things that you are doing during this big event. What related to the things that we are talking about, underground storages and so on, I have a short presentation that I'm going to show directly from my laptop. Hopefully it will work. Cross fingers, okay? Please tell me as soon as you can confirm to me that you can see my screen, please.
Not yet. It's okay.
Okay, I'm going to extend the... Okay. Okay, well, hydrogen underground storages. Well, my short presentation is going to be somehow a follow-up of the previous one that the professor has shown previously, but really focus on the activities that Enagas is conducting in this moment in Spain related to hydrogen market. Well, I have to say that Enagas nowadays is the transmission system operator within the Spanish natural gas market and the technical manager of the gas system. And we have been from many years ago carrying out exploration and investigation to develop underground gas storages, obviously firstly focus on natural gas. Nowadays, we have 3 underground storages working, one in the north coast of Spain, which is an offshore, one in the Pyrenees, which is an onshore one, and the last one that we construct is the Yela underground storage, not really far from Madrid. We have been analyzing more than 100 structures alongside Spain, and we have characterized 14 structures by drilling wells and seismic surveys, taking into account that 4 of them are salt diapirs. Finally, in all of this process, we finally developed these three ones. Okay, two of them are depleted gas fields that were converted into underground storages, the one that is in the north coast of Spain and the one in the Pyrenees. And on the other hand, Gela underground storage is aquifer, saline aquifer, a deep saline aquifer that was constructed for putting natural gas in the underground storage. In all of these activities that I have said previously, we took roughly 12 years from exploration, investigation, and construction. I'm not saying things new for everybody, but it's important to know that when we talk about underground storages, it's a very sophisticated technology that takes time. Takes time for the exploration, obviously doing geological studies, seismic reviews, then investigation, and finally construction and operational and maintenance. When you do all of these activities and probably previously exploration and investigation, the key question is the money that you have to put on the facility without 100% success in the activities that you have to conduct. So as you have seen previously, we have been working for a long time and we have explored all the geological formations in Spain, more than 100. And obviously at the end, we have 3 underground storages with 2 of them are depleted gas fields. When we talk about hydrogen, and now focus on the core business of this panel session, you can see where we are now conducting activities in Spain. As the professor has mentioned previously, obviously we are focused on the possible salt cavities, salt deposits that are located alongside Spain. We have plenty of them in the region, in the north, between Asturias region and Castilla y León region, together with Cantabria region. Then we have in the east, we have in Catalonia region, there are some formations that are under analysis, and in the Mediterranean coast, we are now working close to Murcia with the aim to see if it makes sense to develop underground storages for hydrogen in these areas. In general terms, the salt layers requirements, the depth, it has been mentioned previously. What we are seeing is that we have between 800 and 1,500 meters, and the capability to solubility is less than 25%. The design of the salt cavities that we are now analyzing are with these numbers between 300 and 500,000 cubic meters. The pressure, the operational pressure that we are now as a reference is in a window between 60 bars and 180 bars, and the cushion gas for this type of formation, it's around between 25 and 30%. Okay, and per year you can develop between 6 and 8 year cycles for this application. I think that with these numbers, for me, what is more important to take into account when you do the business case of this type of technology and solution is that you have to take into account that you need at least 30% of cushion gas of the total capacity of the cavity. Okay, so with natural gas we have the same question, but it's obvious that the problem with the hydrogen is the hydrogen itself. Okay, you don't have big amounts of hydrogen by the moment, so if you have to maintain a cushion gas of 30% of the total capacity, is a big amount of hydrogen that can be used for commercial applications. This is something that has to be taken into account when you do the business cases of this type of technology. In the case that you are doing repurpose, okay, because maybe you have formations that are available because are in a mining process or in a company that its activities directly connecting with the selling of salt and so on and so on, obviously you can reduce dramatically the time that you need for conducting all the activities and finally have the ready to use the salt formation for as an underground storage. You can reduce half the time that it's a normal time for this type of activities. You can, in 6 years, can conduct and you can repurpose obviously the infrastructure that you have found obviously for the application of hydrogen. Okay. It has been previously mentioned by the professor. Obviously, the different activities related to the formation of this type of geological structures takes time. And another important issue is the water. The leaching process to create the domo, to create the geological formation, it's something to take into account when you plan this type of formations. Why? Because normally these formations are where they are. And if you need to do leaching and then you have to, the brain and all the salt has to be sent to somewhere, depends on the distance from for example, to the sea or other possible solutions, could be a real problem because you need plenty of water to do the leaching of the cavity and finally to obtain the final volume that you are looking for. This is something to take into account. So the gaps that could be covered in your studies should be that high demand of water. As a reference, we have this type of number, roughly 600 cubic meters per hour by 8 years or 6 years to develop between 8 and 10 cavities. So if you do a number, it's a big amount of water that first you need, and obviously then you have to you have to send it to somewhere, obviously because the environmental impact of this type of water is really high. The brine discharge, it's 10 times sea salinity. So many environmental analysis have to be conducted to guarantee that you are not changing the salinity of the place where you are sending the brine of discharge. Okay, these are the main constraints when you develop a green field from the point of view of saling the upper. Obviously, the mitigation measurements could be seawater to the leach again, or maybe if you have a mining company that are selling salt, then you can do this type of agreement to send them the salt water to be treated by them, and obviously the commercial activity that they can introduce in their commercial activities. From the point of view of seismicity, it has been previously mentioned by the other panelists. There are no big risk. In fact, it's very low risk, I have to say, and which is very important in many areas in Europe, like in Spain. Talking about public concern, this is something that you have to take into account. But for this mitigation risk, we introduce geomechanical models and obviously semaphoric alert systems dedicated with seismographs and other type of EOT solutions to control the formations. And obviously, another important issue that I have mentioned previously is that the social impact. In all of these type of activities, then always you have to conduct many studies, environmental, impact risk, whatever, but the public opinion, it's something that it's really important to take into account, because maybe, could be reluctant to this type of technology to be in the close fence or the house. So it's something that you need to take into account. And this is something that I have to say that is really an important issue to take into account. And just a brief information about regulation in Europe. In the case of hydrogen, now probably many of you knows that are now undergoing discussions in Brussels with the gas package related to natural gas, renewable gases, and hydrogen from the point of view of underground storage and seasonal storage, which is key because it has been previously exposed by other panelists that with this type of formation, you can balance a system that is dependent on the seasonal production of electricity and seasonal production of hydrogen. Obviously, this type of technology solutions, this type of infrastructure should be regulated with the idea to be controlled in a regulated manner in the future European hydrogen backbone. And well, in the case of Enagas, and I'm finishing, obviously, what we are now conducting is a ranking of sites. Obviously, with the ranking of sites, we are conducting seismic surveys, and obviously in the future, drilling campaigns to characterize the formations that obviously will be appropriate for these activities. And obviously, in parallel, we are analyzing the possibility to repurpose some cavities that could be early adopters in this type of technology, and obviously the combination with the dynamics of the hydraulic modelization of the Spanish hydrogen backbone, because it's obvious that when you connect these infrastructures with the pipes, you have to take into account both, and both has to be obviously connected, and obviously from the point of view of operational activities, both of them have to be obviously in line. And it is what it is.
Thank you so much. Thank you so much, Jesús, for this presentation, and also for giving us the chance to know about your experience in the field and Enagas, what you are doing in Spain, and also about the important topics that we should take into account, notably risks and environmental impacts. Thank you so much. We'll get back to you later. Without further ado, I invite Mr. Franck DERRIEN. The stage is yours.
Thank you, Achraf. Hello, everyone. Thanks for giving us the opportunity to present this presentation today. I'm going to make a brief introduction to Storengy, to my company, and then go to the reason why we are convinced that underground hydrogen storage, QHSE, is really key for the future development of hydrogen. The company Storengy is a company of the group ENGIE. We have been in charge of gas storage for decades. Now we are operating 21 storages in France, where we have 75% of the storage capacities, but also in Germany and in the UK. To perform these operations, we have dedicated teams of experts in subsurface who are totally familiar with the risks related to the gas storage and are totally able to ensure a high level of security. More recently, we were interested in H2 storage as well. We decided to develop some projects in salt caverns because it seemed to be the most advanced way to store hydrogen, high volumes of hydrogen, and we turned out to have the possibility to use some of our storage facilities to proceed to this project. So we have actually some projects ongoing. The most advanced one is Achraf. It's on the eastern part of France. It's the blue point just a little bit on above the three other ones. And the project is called Hipster. I'm going to make a brief presentation of this project. It was inaugurated actually last week, so it's quite well advanced. It's not a project which is at its industrial level of maturity. It's a pilot. We are going to continue its implementation, and once we are familiar with all the the questions related to the way to manage this pilot, then we will be able to industrialize it. As said, it's a pilot, so it's not big volumes. We have an electrolyzer of 1 megawatt, and the purpose at this stage is to be able to store 3 tons of H2. And then in the second stage, we will go to 44 tons and be able to commercialize these volumes. Coming back to the very first stage, the stage that will start early next year, we will actually not commercialize the H2 that will be stored, and this is really a first of a kind, and it's you're going to ask me why, since there are already hydrogen storage facilities in the world, not many, but there are some. The fact is that we consider that to add some utility of the storage to the hydrogen economy, we will have to be very flexible, and that will require a capacity to cycle the hydrogen at a much more frequent rapidity than what we currently do for natural gas. So we are going to perform 100 cycling of hydrogen in the first 3 months after the launch of the pilot. That will give us all the information we require to finalize the exact design we want to have for future industrialization of hydrogen storage, and then we will be able to move to the second stage. We are partnering with many different partners. We benefited from European Union subventions for subsidies for this, and we are quite happy with the way it goes. So let's see next year when it really starts, and the outcome of these tests. I'm going to detail why we consider that hydrogen storage is key for the development of hydrogen economy. Just considering the way storage is currently used, if you look at the right, shall we be in a world where we have only natural gas, or in a world where we transform the electricity into hydrogen and then store this hydrogen? The demand will not change too much. So we need to be flexible and be able to adapt to a seasonality of consumption, but also weekly and hourly. You are certainly all familiar with this concept. Regarding what we call production, so what is injected into the storage, the situation is totally different when you are in the world of natural gas and when you are in a world of hydrogen. When you are in a world of natural gas, you have long-term contracts with schedulings and then inject the gas when the time comes that you can then produce at the right season, at the right time, to match with the demand. On the other hand, when it turns to hydrogen, and we have to imagine how it will be in 10 years, 20 years, 30 years, the hydrogen will come from renewable energy production that will mostly be located locally. And we will not be able to decide to have a continuous flow of injection of hydrogen in the storage. We will totally depend on the intermittent energy production that will then help produce hydrogen. So, and that brings us back to the question of cycling and to the importance of cycling. We have to be able to really be able to inject hydrogen when there is a good opportunity of cheap energy, cheap renewable energy, and then produce this hydrogen when it's necessary. But we cannot we will not be able to have a long-term forecast on when it's injected, and this requires a good capacity of cycling of the storages. All in all, we see 5 different reasons why hydrogen is really crucial for the development of the economy of energy. The first one, and it goes to the question of cycling also, is the system. In case you can store hydrogen, then you will have less needs, less obligations to develop a very big infrastructure that can support all the energy production that will be produced when there is a lot of renewable production. It allows also a good arbitrage because the capacity to store cheap energy enables you to use it when you want to use it, and not to have to buy more expensive energy when the market is high. It gives also a strong insurance to the systems to be able to provide the needs and bring energy when it's necessary. Also for environmental reasons, since storing hydrogen will enable to develop locally, and it will necessarily be the case, renewable energy resources, so we will be less dependent on non-renewable energy sources, so that will be virtuous for the environmental. And globally speaking, having storages will be a good way to speed up the pace of development of renewable production. So this is globally very virtuous. I come back to what was said earlier by my colleagues. It takes a long time to develop hydrogen storage capacities. So we have to really to be able to consider how it will be in 5 years' time, 10 years' time, and then start working today. So hipster project in this perspective is really key to us, and we really want to move to implementations very rapidly. This is the last slide. Among the 5 reasons why it's necessary to have hydrogen storage, there is the system. This is the illustration of how the system can be strongly improved thanks to the hydrogen storage. We have taken a case that is, let's say, realistic, knowing that as of today, the economy of hydrogen is not fully developed. So we don't have a global infrastructure that links all together all the different hydrogen utilities. We can compare on this table 2 different systems, considering a local use of an industrial that requires a band of hydrogen for his process. And in case, in the first case on the left side, so without hydrogen storage, let's say this industrial wants to be able to say that his production is green. Then they will go to the market and buy if you see the curves, the green curves, dark green and light green, this is renewable energy. He can go to the market and buy this renewable energy. It totally depends on if there is wind or sun or etc. and of the market prices to be able to run his electrolyzer. And when there is not renewable energy, or when it's too expensive, then he will go to the blue market, where the energy comes from wherever you want, but it can lead to something that is not green, actually, and that is sometimes expensive. On the other hand, when you have hydrogen storage, You can increase the size of your electrolyzer. Then when you have good opportunities of the market, on the renewable market, cheap energy renewable, you can get it and produce more energy than needed for the process. Then the hydrogen can be stored. The remaining hydrogen can be stored. And then you can produce it when the market price is too high. So it can bring significant savings for the system. And in this sense, the storage will help develop the energy of hydrogen. Thank you.
Thank you, Frank, for this presentation. I really like that last slide, which give us the importance of this kind of technology for the hydrogen market. I think that we don't have much time for questions, so I will go for the closing note. As we conclude this session, I think that I hope that we answered some of the questions that needed to be addressed, and our contacts are available on Hoover platform, or also the presentation. So feel free to contact us if you have other question or inquiries. But I'd like to leave you with a thought. Our exploration of this technology of salt cavern storage is not about energy solutions. It's about making a sustainable future for the generations to come. Each one of us has a role to play in this exciting journey toward a cleaner and greener world. So let's remember that innovation, collaboration, and also the commitment to safety will be our guiding stars. Together we can make a lasting impact on our planet and be remembered for our contribution to a better tomorrow. Thank you so much for for being part of this important conversation, and safe travels for our journey and endeavor filled with success and purpose. Thank you all.